Okay then, so this video is just simply an example of the use of Archimedes' principle to work out an unknown. It's a bit of a nice example I've made up, and hopefully something similar comes up in exams, but you'll see the application really more than anything else. So imagine for a second we've got water, iceberg, under the water, and we're told that the volume of this iceberg in total is 250 meters squared, cubed, sorry, apologies. 250 meters cubed. Now, ice has a density of about 900, and water has a density of about 1,000. That's kilograms per meter cubed, so as a unit, we'll just put that in there, kilograms per meter cubed. So here we are with this problem. We want to work out what is the volume of the iceberg under the water. Well, we know that the volume in total is 250 meters cubed. So let's look at this problem from a forces idea. Now we know that there is a force downwards. And that force is created by mass times gravity. We know that there is a force upwards that's created by the upthrust, and that, from the equation from the previous video, is force is equal to V rho G, where, let's be clear on this, V is the volume of the iceberg under the water, and rho is the density of the water. Okay, so that's the density of water that's been displaced by the iceberg under the water. That's what gives rise to the upthrust. So we need to just toy with these values a little bit, just to see if we can make them work for us. So this mg at the bottom here, we don't know the mass of this, but we do know its density, and we know its volume. So as from before, we suggested that mass is equal to the density times the volume. So we can rewrite this force down here, the force downwards, to be F equal V rho G, where V, in this case, is the volume of the iceberg in total, and rho is the density of the iceberg as well. Okay, so just to recap, the upwards force is the force due to the upthrust, where it's the volume of the ice under the water. Put a little U there as well because it's ice under. And the density of the water that's been displaced times by G. Now, as you all know from icebergs, is that the top and the bottom, they float. Okay, it's not sinking, it's not going up. So what you should be able to tell me about these forces is that they are equal to each other. So we can write that V total times the density of the ice times the gravity is equal to the volume of the ice under the water times by the density of the water, that's the water displaced, and gravity again, times by that. So at this stage we can rub out our up and down forces, because I'm going to need this space to do some working. So here we are with our problem. Well, hopefully you should be able to see that I can get rid of my g's, both sides, by dividing both sides by g, and that leaves us with the V total times by the density of the ice is equal to the volume of the iceberg under the water and the density of the water. Rearranging this equation now can lead us to VT rho I over W under the water. So at this stage, we just need to look at it and we can say, okay, we just need to plumb in the numbers now. So we've got 250 times by I, the density of the ice, which is 900, divided by 1,000. And that will equal, if you plumb that into your calculators, $225. Okay, so what we've got here is a situation where we've quite happily worked out our final volume underneath the water, and as you can quite clearly see, as we know from culture about icebergs, most of their density, most of their mass is underneath the water, and we've just proven that aspect through our calculations and our understanding of Archimedes' principle. Okay, so this is what I like to call the iceberg question. There is a quick way of seeing your way through this question. If you've seen it already, brilliant. It's to do with the densities. You can use the densities to do a quick way, but I'd like to see if any of you can see that, and we'll see if you can come up with it for the beginning of the lesson next time. Okay.